In this video, I'm going to show you 3 examples of hypothesis tests. One for population mean, where the population standard deviation is known. One for population mean, when the population standard deviation is unknown. And one for a population proportion. In this video, we are going to go over some examples of performing a hypothesis test. The first example that we're going to go over, the problem is a manufacturer must test that his bolts are 1 centimeter long when they come off the assembly line. He must recalibrate his machines if the bolts are too long or too short. After sampling 49 randomly selected bolts off the assembly line, he calculates the sample mean to be 0.94 centimeters, so a little bit smaller than 1 centimeter. He knows that the population standard deviation is 0.22 centimeters. Assuming a level of significance of 0.10, is there sufficient evidence to show that the manufacturer needs to recalibrate the machines? Now, whenever I'm reading this, I can immediately see that this is going to be a hypothesis test for a population mean, because he is calculating the sample mean, so it tells me he's interested in the mean. And I can already tell you that we're going to be using the normal probability distribution because this person knows the population standard deviation. Now, the first step is for us to state the null and alternative hypothesis. The null hypothesis is HO, and the alternative hypothesis is HA. The null hypothesis always involves equality. So it may be an equal sign, it may be greater than or equal to, or it may be less than or equal to. The alternative hypothesis always involves some sort of inequality. So it's either going to be not equal to, or greater than, or less than. Now, this person says that they're just interested in figuring out whether or not the bolts are too long or too short. So that tells me that he's not specifically interested in whether they're too long or whether they're too short. He just wants to know, are they equal to 1 centimeter or not? Okay, so since this is a hypothesis test for a mean, I know that this is going to involve the population parameter mu. Mu is the Greek letter that represents the population mean. So since I'm interested in whether or not the bolts are too long or too short, I know that this is going to be equal to or not equal to. Since they did not specify that they were only interested in figuring out if the bolts were too long or if the bolts were too short. Now, the bolts are supposed to be 1 centimeter long. So that's the claim that we're testing. So 1.00 centimeters. You can put the units in there if you want to. Now it says determine which distribution to use for the test statistic and then state the level of significance. Now since I know sigma, the population standard deviation, so I'm going to use the normal distribution. And they tell me that the level of significance is 0.10. This is also called the alpha level. Microsoft Word, whenever you type it in there, it kind of compresses the Greek letter alpha. This is really what alpha looks like. Looks kind of like a fish. Right, so our alpha level, or our level of significance, is 0.10. Now, alpha represents our probability of making a type 1 error. So this is basically saying that you're comfortable with making a type 1 error approximately 10% of the time. Right, so alpha is 10.10, so that's 10%. Now it says gather data and calculate the necessary sample statistics. That's step 3. Now I'm going to be using this first row because I'm conducting a I'm conducting a hypothesis test for the population mean, and I know the population standard deviation, so I'm not using these at all. Okay, so here's my standardized test statistic. Now my test statistic is just my X bar, our sample mean X bar. And the standardized test statistic, that's what they're going to be asking you for. Alright, so let's calculate the standardized test statistic. Alright, so that's X bar minus mu over population standard deviation divided by square root of n. Okay, so X bar, that's our sample mean. The sample mean was 0.94. Minus the population mean was 1.00 divided by, and then in parentheses down here we have our population standard deviation 0.22 divided by the square root of the sample size. Let's see, sample size was 49. Now I'm going to put this all in my calculator at one time. And putting this in your calculator at one time, all at one time, is going to help you avoid any rounding mistakes. So let me show you how I'm going to do this. So I can zoom it in a little bit. Okay. Now if you have a TI-84 or above, then you can do this little secret menu that I'm about to show you. I have to pull it back just a little bit so you can see. Alright, so this little secret menu I was just mentioning is where you go to alpha, so hit the alpha button, alpha, y equals. That's going to pop up this little menu of display options for fractions. Right, so, and it has a lot of other options too that we're not using here. It's like functions, matrices, and then y variables. But we're just using this little fraction menu. Right, so hit enter on the first option. That's going to be just a regular fraction. The next one is a complex fraction. Or complex fraction. I think that's what we call those. I haven't used those in a while. Alright, so in the top we have 0.94 minus 1.00. In the denominator, I'm going to put a little parentheses around it just to make it match up, but you don't have to if you're typing it in this way. Right, 0.22 divided by the square root of 49. Get out of that square root and close the parentheses. And hit enter. And there's your test statistic. They typically want you to round this to 2 decimal places. So the test statistic here would be negative 1.91. So the test statistic here would be negative 1.91. Readjust my camera here. Right, so there's our test statistic. So that's the first part of the problem. Is to calculate the test statistic. And now our last step says to draw a conclusion and interpret the decision. Now there are 2 different ways that you can do this. I'll show you one example of each method that you can use. The first method uses rejection regions, and the second method uses p-values. So I'm going to show you how to do this in your calculator using the p-value method. Okay, so you're going to grab your calculator. Okay. Now, the steps are going to be similar to how you construct a confidence interval. So we're going to go to stat and then over to tests. So you're going to scroll over to test right here. Alright, so scroll over 1, 2. Alright, and then it's the first option there, z-test. Alright, so I'm just selecting this first option here, z-test. If we didn't know the population standard deviation, then you would do a t-test. Now it's going to ask you for some information. Just like with the confidence intervals, if you have a data set, you would go to data, and you would need to have that data typed in to your list. And if you don't have a set of data, then you're going to use this stats option. That's what we're going to do. Alright, so our null hypothesis, that value, let me state that again. Our population mean mu was 1.00. Our population standard deviation, they told us, was 0.22. Our sample mean was 0.94. Sample size was 49. And then you're going to want to select what your alternative hypothesis is. Ours is not equal to. And the options here, it gives me an option for a color. That's if you're drawing the distribution with the rejection region. But I'm just going to go to calculate. And there you have it. So it is going to tell you the test statistic and the p-value. Okay. So that kind of kills two birds with one stone. Does all the work for you. So this is what I would suggest doing. Now the downside of this method is you have to be very careful and make sure that you're plugging all of your numbers in correctly. Now here's our p-value. Our p-value is 0.056. Okay, so I'm just going to write that down. P-value 0.056. Now, the rule for drawing a conclusion whenever you are using the p-value method is as follows. These are brand new pens, so I'm having to take the little thing off the bottom. If P is low, reject HO. Okay, so if P is low, reject HO. What that says, what that means, is that if your p-value is less than your alpha level, your level of significance, then reject your null hypothesis HO. Alright, so let's compare our p-value with our level of significance. Alright, so our p-value was 0.056. Remember our alpha level, our level of significance was 0.10. So, take a second and think about this. Is the p-value less than your alpha level? Yes, your p-value is definitely less than your alpha level. If it helps you to convert these to percentages to determine if they're less than or greater than, then you can think like this would be 5.6%, and then alpha would be 10%. So p-value is definitely smaller. So we're going to say reject HO. That's our conclusion. And now we have to interpret the decision. So if we are rejecting the null hypothesis, let's go back up here to where we stated the null and alternative hypothesis. We are rejecting the null hypothesis. Okay, so reject HO. So if we are rejecting the null hypothesis, that says that we have significant or sufficient evidence to believe. I think they use the word sufficient. We'll say we reject HO and conclude there is sufficient evidence I'm running out of room. Sorry about the glare on the camera.
Sorry about the
Right,
glare.
there is sufficient evidence to believe.
Right, there is sufficient evidence to believe
that the mean bolt length is not 1.00 centimeters. At the 0.10 level of significance. It's always important to state your level of significance, especially if you're writing like a scientific paper, and that way, people know what kind of rejection area you were working with. All right, now let's look at another example.
Now let's look at an example when we don't know the population standard deviation. So this example says, a parenting magazine reports that the average amount of wireless data used by teenagers each month is 8 gigabytes. Right, notice that in that sentence they said the average amount. Right, so that we can go ahead and write down now that we're using the mean. Alright, so that's the population mean mu, the Greek letter mu. Alright, so it says, for her science fair project, Ella sets out to prove the magazine wrong. She claims that the mean among teenagers in her area is less than what was reported. Okay, so the magazine claims, that's the null hypothesis, that teenagers use 8 gigabytes a month. Ella claims that they use less than that. So that's going to be less than 8. So the alternative hypothesis is always the claim that you're testing. So the rest of the problem says, Ella collects information from a simple random sample of 16 teenagers, alright, so sample size N is 16, at her high school, and calculates a mean of 7.1 gigabytes per month. So sample mean is 7.1, with a standard deviation S, that's the sample standard deviation, is 2.3 gigabytes per month. Assume that the population distribution is approximately normal. Test Ella's claim at the 0.10 level of significance. Alright, so again, our level of significance is 0.10. That's just a coincidence. It's not always going to be 0.10 for your level of significance. Now, even though they tell us that the population is approximately normal, we still have to use the student's t-distribution because we do not know the population standard deviation sigma. Alright, so since we do not know the population standard deviation, we're going to use the student's t-distribution. Alright, so now let's go down here and calculate our test statistic. Again, we are looking in the middle row because we do not know the population standard deviation. So let's calculate our test statistic t. Alright, so t is equal to x bar minus mu. It's always value minus mean over standard deviation. Here the standard deviation is s divided by square root of n. Again, that comes from the central limit theorem. Alright, so that's equal to x bar was 7.1 minus 8 over, again we're using 8 here because that's the population mean. That's what the parenting magazine reported. S was our sample standard deviation, that's 2.3. divided by the square root of the sample size, which was 16. Alright, now let's plug that in the calculator. So again, I'm going to use this little secret menu, alpha, y equals. If you have a TI-83, then you don't have this menu. But TI-84 and above, you should have that menu. Alright, so numerator is 7.1 minus 8. Just be really careful as you're typing this in. And then denominator is 2.3 divided by the square root of 16. Notice that I used the arrow to get out of the radical in the denominator. Then hit equals. Oh, I have an error somewhere. Let's see. Oh, I had 2 decimal points. Let me delete one of those decimal points, and there we go. Negative 1.57. Negative 1.57. Alright, now we are going to work on drawing our conclusion. I'm going to use the rejection region method for this problem. Now, the rejection region method for the student's t-distribution is significantly more work than just using the calculator. So I would, if you do have a graphing calculator, I would suggest that you use that instead. But here's how you would do this using the rejection region method. So I always start by drawing my distribution. So this is my drawing of the student's t-distribution. Alright, now I'm going to look at my rule for rejection region method. It says rejection regions for hypothesis tests for population means with sigma unknown. It says that we are going to reject HO if t is less than or equal to the negative critical t value for a left-tailed test. Alright, so we are going to do, we're going to have to calculate our critical t value. Alright, so you could use the table for this. Let me see, I actually have a t table right here so I can show you. You could also use your calculator to look up the inverse t value, but if you had your calculator, again, I would just suggest that you use the calculator to determine your p-value. Alright, so our sample size was 16, so that tells us we are going to be looking at this row right here with 15 degrees of freedom. Alright, this is a left-tailed test. So, let's see, area and one tail. This was a 0.10 level of significance. So that tells us that the area in the left tail is going to be 0.10. So there we go. So again, we're using area and one tail. And we're just finding the intersection of that row and column. There's our critical t value. And it might be hard to read. It's 1.341. And again, we're supposed to be using the negative version of that according to that table. So that's negative 1.341. The middle here is 0, so I'm just going to mark that. Okay, now let's mark our test statistic. Our test statistic was negative 1.57. Well, first, before I do that, let me just highlight the rejection region. So the rejection region is, we're going to reject HO if it's less than this value. Alright, so that's our rejection region that I have colored in there. So, if our test statistic is negative 1.57, does the test statistic fall in the rejection region? It does, because if we were to plot this value on this student's t-distribution, it would probably be about right around here or so, not very far from our test statistic, or excuse me, our critical t value. So it's negative 1.57. And so since it is in the rejection region, we are going to reject HO. Alright, so now we have to interpret the decision. So we'll say we reject HO and conclude that there is sufficient evidence to believe, or to support, you could also say that, to believe that at the 0.10 level of significance, the average amount of data used, running out of room again, by teenagers each month is less than 8 gigabytes. Kind of got out of the frame there. There we go. Sorry about that. Alright, so there's our interpretation. We reject HO. We conclude that there is sufficient evidence to believe that at the 0.10 level of significance, the average amount of data used by teenagers each month is less than 8 gigabytes. Alright, so now we've gone through an example with both versions of our hypothesis test for population mean, where we do know the population standard deviation and where we do not know the population standard deviation. So now let's look at a hypothesis test for a population proportion.
Now let's look at an example when we don't know the population standard deviation. So this example says, a parenting magazine reports that the average amount of wireless data used by teenagers each month is 8 gigabytes. Right, notice that in that sentence they said the average amount. Right, so that we can go ahead and write down now that we're using the mean. Alright, so that's the population mean mu. It's the Greek letter mu. Alright, so it says, for her science fair project, Ella sets out to prove the magazine wrong. She claims that the mean among teenagers in her area is less than what was reported. Okay, so the magazine claims, that's the null hypothesis, that teenagers use 8 gigabytes a month. Ella claims that they use less than that. So that's going to be less than 8. So the alternative hypothesis is always the claim that you're testing. So the rest of the problem says, Ella collects information from a simple random sample of 16 teenagers, right, so sample size N is 16, at her high school, and calculates a mean of 7.1 gigabytes per month. So sample mean is 7.1, with a standard deviation S, that's the sample standard deviation, is 2.3 gigabytes per month. Assume that the population distribution is approximately normal. Test Ella's claim at the 0.10 level of significance. Alright, so again, our level of significance is 0.10. That's just a coincidence. It's not always going to be 0.10 for your level of significance. Now, even though they tell us that the population is approximately normal, we still have to use the student's t distribution because we do not know the population standard deviation sigma. Alright, so since we do not know the population standard deviation, we're going to use the student's t distribution. Alright, so now let's go down here and calculate our test statistic. Again, we are looking in the middle row because we do not know the population standard deviation. So let's calculate our test statistic t. Right, so t is equal to x bar minus mu. It's always value minus mean over standard deviation. Here the standard deviation is s divided by square root of n. Again, that comes from the central limit theorem. All right, so that's equal to x bar was 7.1 minus 8 over, again we're using 8 here because that's the population mean. That's what the Parenting magazine reported. S was our sample standard deviation, that's 2.3, divided by the square root of the sample size, which was 16. All right, now let's plug that in the calculator. So again, I'm going to use this little secret menu, alpha y equals. If you have a TI-83, then you don't have this menu, but TI-84 and above, you should have that menu. All right, so numerator is 7.1 minus 8. Just be really careful as you're typing this in. And the denominator is 2.3 divided by the square root of 16. Notice that I used the arrow to get out of the radical in the denominator. Then hit equals. Oh, I have an error somewhere. Let's see. Oh, I had 2 decimal points. Let me delete one of those decimal points, and there we go. Negative 1.57. Negative 1.57. All right, now we are going to work on drawing our conclusion. I'm going to use the rejection region method for this problem. Oops. Now, the rejection region method for the student's t-distribution is significantly more work than just using the calculator. So I would, if you do have a graphing calculator, I would suggest that you use that instead. But here's how you would do this using the rejection region method. So I always start by drawing my distribution. So this is my drawing of the student's t-distribution. All right, now I'm going to look at my rule for rejection region method. It says rejection regions for hypothesis tests for population means with sigma unknown. It says that we are going to reject HO if t is less than or equal to the negative critical t value for a left-tailed test. All right, so we are going to do, we're going to have to calculate our critical t value. All right. So you could use the table for this. Let me see. You actually have a t-table right here, so I can show you. You could also use your calculator to look up the inverse t value, but if you had your calculator, again, I would just suggest that you use the calculator to determine your p-value. All right, so our sample size was 16, so that tells us we are going to be looking at this row right here with 15 degrees of freedom. All right, this is a left-tailed test. So let's see, area and one tail. This was a 0.10 level of significance. So that tells us that the area in the left tail is going to be 0.10. So there we go. So again, we're using area in one tail. And we're just finding the intersection of that row and column. There's our critical t value. And it might be hard to read. It's 1.341. And again, we're supposed to be using the negative version of that according to that table. So that's negative 1.341. The middle here is 0, so I'm just going to mark that. Okay, now let's mark our test statistic. Our test statistic was negative 1.57. Well, first, before I do that, let me just highlight the rejection region. So the rejection region is, we're going to reject HO if it's less than this value. All right, so that's our rejection region that I have colored in there. So if our test statistic is negative 1.57, does the test statistic fall in the rejection region? It does, because if we were to plot this value on this student's t-distribution, it would probably be about right around here or so, not very far from our test statistic, or excuse me, our critical t-value. So that's negative 1.57. And so since it is in the rejection region, we are going to reject HO. Alright, so now we have to interpret the decision. So we'll say we reject HO and conclude that there is sufficient evidence to believe, or to support, you could also say that, to believe that at the 0.10 level of significance, the average amount of data used, running out of room again, by teenagers each month is less than 8 gigabytes. Kind of got out of the frame there. There we go. Sorry about that. Alright, so there's our interpretation. We reject HO, and we conclude that there is sufficient evidence to believe that at the 0.10 level of significance, the average amount of data used by teenagers each month is less than 8 gigabytes. Alright, so now we've gone through an example with both versions of our hypothesis test for population mean, where we do know the population standard deviation and where we do not know the population standard deviation. So now let's look at a hypothesis test for a population proportion. Alright, let's look at our last example. This is going to be a hypothesis test for population proportion. Alright, so let's find an example. Alright, so it says, postpartum depression and anxiety, PPD, is a common medical condition affecting mothers and their families after the birth of a baby. The CDC estimated that 14% of women who have recently given birth suffer from PPD. Okay, so again, we can already tell that this is going to be a hypothesis test for population proportion because they're using a percentage. Right, so I can go ahead and draw in P for the population proportion. The claim says that 14% of women who have recently given birth suffer from postpartum depression. So it's going to be P equals 14% as a decimal is 0.14. Says, however, this research only reflected self-reported cases. Therefore, one group dedicated to helping women and their families with PPD believe that the true percentage of women who suffer from PPD is much higher. Right, so since they think it is higher, our alternative is going to be that it's greater than 14% as a decimal. The group conducts a simple random sample of 116 women. So there's your sample size. 116 women who had given birth in the last year, and discovers that 22 of them reported having PPD. Alright, so there's our sample proportion, 22 out of the 116. Based on this evidence, can the group claim that the true percentage of women who have PPD is greater than 14%? Use a 0.05 level of significance. So there's your level of significance. Alright, so again, I don't have that little table because I ran out of copies of that outline. But you're going to use the normal distribution here because it's a population proportion. You could go through and like verify all the conditions, but I'm going to skip that here just in the just for the time purposes. Now we are going to calculate the test statistic. You should recognize this test statistic from the when we talked about confidence intervals. Alright, so P hat, that's our sample proportion. We can go ahead and just see what that is as a decimal. Maybe it's a nice decimal number. 22 divided by 116. Oh, no, it's not. So whenever you have a situation like this where you have this really long decimal, don't round that. Just leave it as a fraction. Okay, so because we don't want to make any rounding mistakes. So 22 over 116, that's our sample proportion, minus 0.14, that was our population proportion, divided by, right now, really long one here. P is our population proportion, so that's 0.14 times 1 minus 0.14 divided by our sample size, which was 116. Okay, now you're going to want to plug this in your calculator. Again, I would suggest taking your time and plugging this all in at once so that you can avoid any rounding mistakes. Alright, so clear everything out. Start with a clean slate. Alright, now I'm going to show you how to do this if you do not have this little fancy button that allows you to go into the display mode. Alright, so here's our numerator. Got parentheses 22 over 116 minus 0.14. Close parentheses. That's your numerator. Divided by the square root. Alright, now we have a fraction inside of the square root. So again, I'm going to put a parentheses around my numerator. 0.14 times parentheses 0.14. I put the 0 here on the 0.14, but I didn't put it there. It doesn't matter. Alright, close that parentheses. Now close the numerator parentheses. Divided by sample size 116. Alright, get out of that and then hit enter. There is your test statistic, 1.54. Whoops. 1.54. Now that it takes practice to be able to plug that all in at one time. Don't get frustrated if you can't get it all plugged in on the first try. Just keep practicing. If you need any help figuring out if you're making a mistake somewhere, just send me a picture of your calculator screen and I can help you. Alright, now we are going to draw our conclusion. Now, I've already shown you an example with the rejection region. I'm going to show you how to use the calculator to conduct this hypothesis test. And it's going to calculate the test statistic for you. So you could skip that last step. Alright, so you're going to go to stat, and then you're going to go over to test. Okay, so scroll over to test. Alright, and this is going to be a 1 proportion Z test. Alright, see it's right there. Option number 5. 1 proportion Z test. Alright, hit enter. Alright, our population proportion was 0.14. Alright, this is this is how they're going to ask you for your sample proportion. So X is going to be the number of successes. So X here is going to be the number of people that had postpartum depression. So that was 22. Our sample size was 116. our proportion. Let's see, our alternative hypothesis was that it was greater than 0.14. So scroll over and select that. Then go down to calculate. Again, if you hit draw, it's going to draw you the little rejection region, if you prefer that method. Alright, so we're going to hit calculate, and there we have it. There's our p-value. Alright, so here's again our test statistic, 1.54. And then our p-value is 0.062. Okay, so let's write that down. P-value equals 0.062. Readjust my camera a little bit. Now remember the rule for p-values. If p is low, reject HO. Alright, so again, you are comparing your p-value to your level of significance, alpha, which they told us was 0.05. So look at your p-value. Is your p-value less than your alpha level? No, it is not. The p-value here is greater than your alpha level. So since it's not lower, we are not going to reject the null hypothesis. So that means we are going to fail to reject HO. So that is our conclusion. Now we are going to interpret our conclusion. Okay. We're going to say we fail to reject HO. We conclude that we do not have sufficient evidence to believe that more than 14% of women suffer from PPD, postpartum depression, at the 0.05 level of significance. Again, you always want to include that level of significance in your interpretation.